Dr. M.P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematics. The topic which we are going to discuss now is integer programming problem. First, we are going to talk about algorithm, namely Gomerion's cutting plane method or Gomerion's fractional cut for solving an integer programming problem. The next idea is, with the help of this Gomerian cutting plane method, we are going to solve an integer programming problem. First, let me define what we mean by integer programming problem. A linear programming problem in which some or all the variables in the optimal solution are restricted to assume a non-negative integer value is called integer programming problem. So, a integer programming problem is a linear programming problem in which some or all the variable restricted to assume a non-negative integer value. In many situations, that is in business and industry, the decision variable will be meaningful only if it assumes a non-negative integer value. Suppose in industry producing 5.83 chairs and open 5.83 bank account is not meaningful. So, in such a case, if the decision variable takes an integer value, it has a meaningful one. Therefore, an integer programming problem is a one in which all the decision variable or some of the decision variable are restricted to assume a non-negative integer value. So, an integer programming problem is a linear programming problem in which all decision variable xi's or some decision variable xi's are restricted to assume a non-negative integer value. So, a integer programming problem is a linear programming problem in which some or all the decision variable are restricted to assume a non-negative integer value. The next idea is, what is a all integer programming problem or pure integer programming problem? All integer programming problem is an integer programming problem in which all the decision variable are assumed to be a non-negative integer value. So, in a linear programming problem, if all the variables in the optimal solutions are restricted to assume a non-negative integer values, then it is called pure integer programming problem or all integer programming problem. So, a pure integer programming problem is a one in which it is an integer programming problem IPP in which all the decision variable, all xi's are non-negative integer value. So, in a integer programming problem, if all the decision variable are assumed to be non-negative integer, such an integer programming problem is called all integer programming problem or pure integer programming problem. The next idea is mixed integer programming problem. A mixed integer programming problem is an integer programming problem in which some of the variables are restricted to assume non-negative integer value and the remaining variables are restricted to assume any non-negative value. Such a problem is called mixed integer programming problem. So, a mixed integer programming is one which is a linear programming problem in which some of the variables in the optimal solutions are restricted to assume a non-negative integer values. So, in a linear programming problem, if some of the variables are restricted to assume non-negative integer value and the remaining variables are free to take any non-negative values, then such a integer programming problem is called mixed integer programming problem. Then we have another one integer programming problem which is called 0-1 integer programming problem, in which all the decision variable is restricted to assume either 0 value or 1 value. Such a problem is called 0-1 integer programming problem. So, with this definition of all integer programming problem, mixed integer programming problem and 0-1 integer problem, let me introduce what we mean by general integer programming problem. So, a general integer programming problem can be written as maximum of z equal to Cx subject to the constraints that Ax less than or equal to B and x all x are greater than or equal to 0 and all x or some x restricted to assume a non-negative integer value. So, a general integer programming problem can be written as maximize z equal to Cx, which is an objective function subject to the constraint that Ax less than or equal to B, in which all the decision variables are non-negative, all x or some decision variable as restricted to assume a non-negative integer value. So, a general linear programming problem, integer programming problem can be generalized in this way: maximum z equal to Cx subject to the constraint Ax less than or equal to B, x greater than or equal to 0, all x or some x or assumes non-negative integer value. With this basic definition of general integer programming problem, now we try to discuss about a algorithm, namely Gomerian's cutting plane algorithm to solve a integer programming problem. In the Gomerian cutting plane algorithm, the first step is we have to convert all the minimization IPP into that of maximization if it is a minimization form and ignore the integrality condition. The first step of Gomerian algorithm is we have to convert all the minimization integer programming problem into that of maximization if it is a minimization form, and we should ignore the integrality condition. The next step, step 2 is introduce slack variable and or surplus variables if necessary to convert the inequation into equation and obtain optimum solution to the given LPP by simplex algorithm. So, the next step of integer programming problem is we have to introduce either slack variable or surplus variable in order to convert all the inequation constraints into equation and solve the standard LPP using usual simplex method. The next step is test the integrality of the optimal solution. Next, we have to test the integrality of the optimal solution. If all xbi greater than or equal to 0 and or integer, then an optimum solution is obtained. Next step is if all xbi greater than or equal to 0 and at least one xbi is not an integer, then we have to go to next step. So, step 3 of the Gomerian cutting plane method is we have to check the integrality of the optimal solutions. If all xbi value is greater than or equal to 0 and all xbi's are integer, then the optimal solution to the given problem is obtained. If at least one xbi is not an integer, then we have to go to next step. The next fourth step is rewrite each xbi as x by I equal to integral part of xbi plus fi, where the box xbi is the integral part of xbi and fi is the positive fractional part of xbi, in which our fi takes the value in between 0 and 1. So, if any xbi is not an integer, then we have to write that xbi as x by I equal to integral part of xbi plus fractional part of that xbi, which we name it as fi. Here the restriction on fi is it is a fractional part, it lies between 0 and 1. After rewriting this xbi as integral part of xbi plus fi, next we have to choose the largest fraction of xbi, that is we have to choose the maximum fi. In case of time, we can select that fi arbitrarily. So, we will let it maximum of fi as fk to the corresponding xbk. This row is called source row. So, if at least one xbi is not an integer, then we rewrite that xbi is integral part of xbi plus fi. We have to do it for all xbi which is not an integer. Then among all xbi, after writing in this form, we choose the maximum fi, let it be fk. The corresponding kth row is called source rows of the given simplex table. So, the fifth step is, suppose we have a negative fraction in the source row, that is, if we assume suppose minus 1 by 7 is there, then we should write this negative fraction as sum of negative integer and non-negative fraction, which we will write it as minus 1 plus 6 by 7. So, we will write the negative fraction as sum of negative integer and non-negative fractions. The next step 6 is find the fractional cut constraints, that we call it as Gomerian constraints. From the source row, we have this equation summation a k j x j, j varies from 1 to n equal to x b k. Now, we rewrite this equation as this equation, in which write a k j as integral part of a k j plus f k j into x j. Then we will write x b k as integral part of x b k plus f k. From this equation, we write it as summation f k j x j greater than or equal to f k. This is called Gomerian constraints, fractional cut constraint. From this, by multiplying this inequation by minus 1, we will get this equation. Now, in this inequation, if we introduce a slack variable gs, then this equation can be written as this way. Here this gs is called Gomerian slack. We will write the source row as this way, summation a k j x j equal to x b k. From this equation, by rewriting a k j as integral part of a k j plus f k j and x b k as integral part of x b k plus f k, we will get this equation. From this equation, we have this equation summation j equal to 1 to n f k j x j greater than or equal to f k. Now, by multiplying this inequality by minus sign, we will get this equation. Now, by introducing a Gomerian slack in this inequation, now this inequation become summation f k j plus gs equal to minus f k. This gs is called Gomerian slack. This constraint is called Gomerian constraint or fractional cut constraints. After obtaining that fractional cut constraints, the next idea is we have to add that fractional cut constraint, that Gomerian constraints obtained in step 6 at the bottom of the optimum simplex table obtained in step 2. Once we obtain the Gomerian constraint, we have to add that constraint in the bottom of the simplex table obtained in step 2. After adjoining this Gomerian constraint in the table, now we have to find a new feasible optimum solution using dual simplex method. And the next step is go to step 3 and repeat the procedure until an optimum integer solution is obtained. Let us have a break. The idea in Gomerian's cutting plane algorithm is, first we convert the given IPP into standard form, then by using simplex algorithm we have to find the optimum solution to the given integer programming problem by ignoring the integrity conditions. The next idea is, next we have to construct a Gomerian constraints. After obtaining Gomerian constraint, the final idea is we have to obtain the optimum solution using dual simplex method. The first idea is, by temporarily ignoring the integrity condition, by applying simplex algorithm, we try to obtain optimum solution to the given integer programming problem. The next idea is forming a Gomerian constraints. After forming Gomerian constraints, now we have to solve the remaining IPP by making use of dual simplex method. This is the idea about Gomerian's cutting plane methods. in a Gomerian cutting plan method how to construct the Gomerian constraints. For that we consider an example. Suppose at any point of time assume this is our simplex table. Now, if we observe the x 1 value which is 4 by 7 and x 2 value which is 12 by 7, both are not an integer. Now, we rewrite this 4 by 7 as integral part of something plus fractional part. We will write 4 by 7 as 0 plus 4 by 7. So, if we consider this as our xbi, now I will write xbi as integral part of xbi plus fi, where fi is a fractional part, fi value lies between 0 to 1. Now, if we take this 12 by 7, we can write this 12 by 7 as 1 plus 5 by 7. So, if we take this is our xbi, now I will write this xbi as integral part of xbi plus fi, where fi is a fractional part. Now, from these two equation, now we have to choose the maximum fi. So, here the maximum fi is maximum of f1 and f2. f1 is 4 by 7 and f2 is 5 by 7. So, from this the maximum is 5 by 7, the corresponding row is this one. Therefore, we call this row as a source row. The maximum value 5 by 7 occurs corresponding to x 2 value. Therefore, this is our source row. From the source row, we can write 12 by 7 as 1 plus 5 by 7, which can be written as 0 into x 1 plus 1 into x 2 plus minus 1 by 7 into s 1. So, from the source row we have this expression. In the source row, if any negative fraction is there, we should write this negative fraction as sum of negative integers and positive fraction. Therefore, this equation can be written as 1 plus 5 by 7 equal to x 2. Now, I will write this minus 1 by 7 as minus 1 plus 6 by 7 s 1. So, this negative fraction can be rewritten as sum of negative integer and non-negative fraction. From this, our Gomerian constraint is 6 by 7 s 1 greater than or equal to 5 by 7. So, this is the way we should construct the Gomerian constraint from the optimum simplex table. If any xbi is not an integer, write those xbi as integral part of xbi plus fractional part. Among all fractional part, you choose the maximum. The corresponding row is called source row. In the source row, any of the negative integer fraction is there, rewrite it as sum of negative integer and non-negative fraction, and from this if we rewrite the fractional cut, that cut is called Gomerian cut or Gomerian constraints. Now, with this algorithm, we try to solve a problem. Solve the integer programming problem. Maximize z equal to x 1 plus x 2 subject to the constraints 3 x 1 plus 2 x 2 less than or equal to 5 and x 2 less than or equal to 2, x 1 and x 2 are non-negative and are integer. So, this integer programming problem involves two decision variable in which all the decision variable are restricted to assume integer value. Therefore, given problem is all integer programming problem or pure integer programming problem. Now, with the help of Gomerian algorithm, we try to solve this problem. For that, first we have to rewrite the given integer programming problem in a standard form by ignoring the integrality conditions. So, the first constraint is 3 x 1 plus 2 x 2 less than or equal to 5. Now, by introducing a slack variable in this constraints, we can rewrite this constraint as 3 x 1 plus 2 x 2 plus s 1 equal to 5. The next constraint is x 2 less than or equal to 2. So, we rewrite this second constraint as 0 x 1 plus 1 x 2. By adding a slack variable s 2, we rewrite this equation as equal to 2. So, here the decision variable x1, x2 and the slack variable s1, s2 all are non-negative and the decision variable x1, x2 are integer. Now, the corresponding objective function for this IPP is maximize z equal to x1 plus x2 plus 0 s1 for slack variable 1 and 0 s2 for slack variable 2 subject to the constraint this one. So, the given IPP first rewritten in this form, which is called the standard form of the given IPP. In the IPP, we ignore the integral condition x1 and x2 are integers. Temporarily, by ignoring the integrality condition, by considering the given IPP as LPP, convert the given LPP into the standard form. Now, we try to solve this LPP using simplex method. So, for that we should go for initial table, where yb is the basic variable. The given IPP which is in standard form have initial basic feasible solution as 5, 2 for S1, S2. So, for the given linear programming problem, the initial basic feasible solution is S1 equal to 5, S2 equal to 2. Now, go for the initial iteration for the given linear programming problem, where S1 and S2 are basic variable. The cost of S1 is 0 and cost of S2 is 0. Now, the right hand side first constant is 5, for the second equation constant is 2. These are the coefficient in the first constraint, x1 coefficient value 3, x2 2, s1 1 and s2 0. For the second constraints, after introducing the surplus variable s2, the corresponding coefficients are 2, 0, 1, 0, 1. Now, in this initial iteration, now we try to improve the given initial basic feasible solution to the optimal solution. For that, first we have to compute Zj. Zj is summation Cb Yj. So, for x1 my Zj is 0 into 3 plus 0 into 0, which is 0. So, for x1 my Z1 is 0 into 3 plus 0 into 3, which is 0. Then for x2 my Z2 is 0 into 2 plus 0 into 1, which is 0 plus 0, again 0. Since S1 and S2 are in basic, we no need to compute the Zj minus Ej and values. So, these are in basic, therefore, we no need to compute Zj minus Ej value for a basic variable. Now, the cost for the variable x1 is 1, because the given objective function is maximum z equal to x1 plus x2. Therefore, cost of x1 is 1 and cost of x2 is 1. Therefore, x1 x2 is 1. Now, from this we will find Zj minus Ej. So, for x1 Z1 minus E1 is 0 minus 1 minus 1. Here 0 minus 1 minus 1. So, in this initial simplex table, if all Zj minus Ej value greater than or equal to 0, then optimal solution is obtained. But as far as this problem concerned, we have 2 Zj minus Ej value is negative. In such a case, we have to improve the optimal solutions. Since both the values are equal, we can choose arbitrarily any one value. Let me choose the variable x1. I will choose this minus 1. Therefore, my x1 enters the basis. So, this is the variable which enters the basis. Once we fix the entering variable, next we have to compute the minimum ratio of xbi by yir, where yir is strictly greater than 0. So, once we fix the x1 entering variable, now we have to compute xbi by yir. So, first one is 5 by 3. For the second one, yir should be strictly greater than 0, but here yir is equal to 0. Therefore, no need to compute that minimum xbi by yir for this S2. Therefore, we have only one value 5 by 3. Therefore, the corresponding variable S1 leaves the basis. So, for this problem, the entering vector is x1, x1 enters the basis and S1 leaves the basis and this 3 is called pivot element. So, with the help of simplex algorithm for the initial iteration, x1 is the entering variable and S1 is the leaving variable and pivot element is 3. Now, we have to convert this pivot into 1 and the remaining element in that column as 0. The next idea is we have to convert this 3 as 1 in such a way that if we divide the row R1 by 3, we will get the new row R1 dash. So, if we divide by 3, the first row becomes 5 by 3 and 3 by 3 1 and 2 by 3, then 1 by 3 0. Now, we have to make the remaining element in the column as 0, which is already 0. Therefore, our new row R2 dash is simply the R2, which we have 2 0 1 0 1. Now, in the next first iteration, our S1 leaves the basis and x1 enters the basis. So, instead of S1 in the first iteration, we have the basic variable x1 is in the basis and S2. The corresponding cost of x1 is 1 and the cost is 0. So, in the next iteration, we have the table in which our basic variable is x1 and S2 and all the coefficient becomes in this way. Now, we will continue this idea in the next session by obtaining the optimal solutions. Now, let me recap of the points what we discussed so far. A integer programming problem is a one in which all the decision variable or some of the decision variable are restricted to assume a non-negative integer value. So, integer programming problem is a linear programming problem in which either some variable or all variable restricted to assume a non-negative integer value. In an integer programming problem, if all the decision variables are restricted to assume integer value, such a problem is called all integer programming problem. Only some of the decision variable is restricted to assume non-negative integer value and the remaining variable are free to assume any non-negative value. Such a linear programming problem is called mixed integer programming problem. If all the decision variables restricted to either assume 0 or 1, such a integer programming problem is called 0-1 integer programming problem. Now, a integer programming problem can be solved with the help of Gomerian cutting plane algorithm. In this algorithm, the first idea is by ignoring the integrality condition, we rewrite the given integer programming in a standard form, then we should solve the given linear programming problem using simplex method. The next idea is if at least one xbi is not an integer, then from this we have to construct a Gomerian fractional cut. After identifying the Gomerian fractional cut, we should add that Gomerian constraints into the optimum simplex table. In the bottom we should attach the Gomerian constraints. After that, we have to make use of dual simplex method, and with the help of dual simplex method, we will try to obtain the optimal solution to the integer programming problem. So, in solving integer programming problem, the main 3 steps are apply simplex method and try to obtain the optimum solutions. If at least one decision variable is non-negative, construct Gomerian constraint for such a problem. After constructing Gomerian constraints, use dual simplex method and try to obtain optimum integer solution to the given problem. So, in a brief, the first idea is solve the integer programming problem by considering linear programming problem by ignoring the integrality conditions and use simplex algorithm. The next idea is introduce Gomerian constraint one after the other. The third and final step is solve the resulting LPP using dual simplex algorithm and obtain optimum integer solution. Thank you.